Today's lesson is on distance, velocity, and acceleration. The first thing that I'd like you to do for your warm-up is to find the second derivative for the function f at x. So that means you need to find the first derivative and then go ahead and find the derivative of the first derivative and then evaluate it at the second derivative at 2. Then I'd like you to find the second derivative of that second function, y equals 1 over x minus 1. So go ahead and pause the video and then start replaying, and I will show you the answer and you can see if you're right. Here you can see your answer for part A should be 2, and your answer for part B, you should get 2 over x minus 2 all cubed. Let's just take a minute to remember that instead of using y prime, we could also use dy over dx, so the derivative of y with respect to x. And when we're taking a look at the second derivative, you might see as well d squared y over dx squared. Now we're going to focus on the vectors, displacement, velocity, and acceleration, and how they're connected. So we're going to first start by defining each of these. Displacement, as we know, is the distance and direction an object has moved from its origin over a period of time. So let's go ahead and fill that box in. Our velocity is the rate of change of displacement with respect to time. So let's fill that in. And then lastly, we can take a look at the acceleration, which we know is the rate of change of velocity with respect to time. So going back to displacement, we commonly write s at t to describe the position or the displacement. So we'll have a function written as s at t, and common units for our displacement is we usually look at meters. You can also look at kilometers, but any kind of distance measure would be fine. Then when taking a look at velocity, we usually write v at t. So velocity with respect to time, and then our units for that would be meters per second or sometimes kilometers per hour. And then for acceleration, we usually write a at t, and again our common units would be meters per second squared or kilometers per hour squared. When we take a look at now velocity, we can take a look at our average velocity, or we can also take a look at our velocity at a particular time. So when we're coming up with our average velocity, we're looking at that velocity over a span of time. So this would be equal to the change in s, or displacement, over the change in time. Or we can look at it as S2 minus S1 over T2 minus T1. Our average acceleration would be similar in that we take a look at the difference in velocity over the difference in time. So our average acceleration equals our change in velocity over our change in time, or similarly we can do v2 minus v1 over t2 minus t1, and both of these we know represent our average rates of change, and we calculated those in MHF last semester. Our velocity we know is v at t, and we also know that this is the derivative of s at t. So that would be our velocity at a particular time. And then our acceleration with respect to time, I know, is equal to the derivative of v at t, which we should also recognize is the second derivative of s at t. And just as a quick reminder, that displacement, velocity, acceleration are all vectors. All of these quantities have both magnitude and direction. We're going to go back and remind ourselves about the difference between a scalar and a vector. So I'm going to have you pause the video and just go ahead and write down S or V beside each of these to determine whether it's a scalar or a vector, and then I want you to play the video and I will have the answers written down for you, and hopefully you get them all right. Okay, so there you go, and just as a reminder, as we're moving forward, when we're taking a look at displacement, velocity, acceleration, all of those are considered vectors. Now let's take a look at an example. So we have a hammer dropped from a height of 90 meters. We have the height of the hammer S after t seconds modeled by our function there, S at t, and just take note that t is greater than or equal to 0. So we're going to find the average velocity of the hammer between 1 second and 4 seconds. So we're looking for the average rate of change between 1 and 4. So we know that our average velocity equals our change in height over our change in time. So that's equal to S at 4 minus S at 1 all over 4 minus 1. So I get 11.6 minus 85.1, and we should be good with subbing in our values and evaluating. We get all over 3, which gives me negative 24.5. And our conclusion is the important part. So therefore, the hammer is falling down at a rate of 24.5 meters per second. So again, we need to make sure that we have direction and magnitude for both of these. The next part is that we're going to determine the velocity of the hammer at 1 second and 4 seconds. So we're looking for the instantaneous rate of change at 1 second and 4 seconds. So I know if I'm looking for v at t, so the velocity at 1 second, that this is equal to the derivative of s, and I know the derivative of s is equal to negative 9.8 t. And so then if I'm looking for v at 1, I'm just going to sub in 1 for t, and that gives me negative 9.8. So my conclusion is, therefore, the velocity of the hammer at 1 second is 9.8 meters per second downwards. Our next question asks us, when will the hammer hit the ground? So this just means when is height equal to 0. So we can use our original function and plug in 0 for s at t. And when I rearrange and solve, I'm going to end up with t is equal to, approximately equals to, plus or minus 4.3. But we have to remember here that we're only going to take the positive one because t is greater than or equal to 0, and that was defined at the beginning. So now we're going to write our conclusion. And our conclusion is that therefore the hammer hits the ground at approximately, because we did have to round, 4.3 seconds. Next, we're going to determine the impact velocity of the hammer. So our impact velocity is the velocity upon impact. So when it hits the ground, we want to know what the velocity is. So we are going to find velocity at the time of impact. And the time of impact we know is approximately 4.3 seconds. So we want to find v at 4.3, which I know is equal to the derivative of s at 4.3. So we can take our v at t equation and sub in 4.3. So I'm at negative 9.8, and instead of t, I have 4.3. And this is going to equal to negative 42.14. So therefore, the impact velocity is 42.14 meters per second down. So that's the velocity as it hits the ground. Now we're going to find our acceleration function, which we know is just the derivative of our velocity function, and then take notice of what it is and interpret it. So our s at t, let's start with that, we know is negative 4.9 t squared plus 90. I did rearrange it. Our v at t is equal to our derivative of s, which is equal to negative 9.8 t. Now let's find our acceleration with respect to time, which I know is the derivative at v, which is the second derivative of s, which equals negative 9.8. So this is our our acceleration ends up being a constant. So we say that we have a constant acceleration of 9.8 meters per second squared down. And what this means, or interpreting this, is that this is actually the acceleration due to gravity, so it should be familiar to us. So let's just go ahead and write that. This is the acceleration due to gravity. Our next example, I'm going to actually have you complete on your own and bring to class with your answers, and we'll go over them and we'll talk about them as a class. So this is a similar question where we have height at t, so s at t, where t is in seconds and then height is in meters. So first I want you to find the initial velocity. So we're going to have to find v at t and then go ahead to solve that when t is equal to 0. So that's your first job. And then your second part is determine the maximum height of the ball. So we do have a quadratic, so we could go ahead and kind of figure that out in a few different ways. But let's just recognize here that if we have a maximum height, that means our velocity is going to equal 0 at that place, right? So all we really need to do is solve for when v at t equals to 0. And then we do have a part C. Part C is where I want you to determine the average acceleration between 1 second and 3 seconds. So we're going to remember that our average acceleration is equal to the change in v over the change in t, and we're going to look at that between 1 second and 3 seconds. So if you can complete this example and then bring it to class, we'll compare them and then we'll get to work and you can ask me any questions then. I hope that this was pretty straightforward and we'll see you tomorrow.